Okay, so here is another example for class number 12. This is video 3. And now we have a 2.5-inch diameter flow nozzle installed. So it's a nozzle. The other one was an orifice example. This is a nozzle example. It is 3.8-inch diameter pipe that carries water at 160 degrees Fahrenheit. We might need to look up what those properties are, by the way, at 160 degrees Fahrenheit, because with a higher temperature, we'll have a different viscosity of the water. Just so you know, we can look that up in a book. If the air water manometer used, right, so what this is describing, I should mention, is sort of a manometer that goes upside down this way, where they're going to have, this is going to be at a high level. There's going to be air inside here, so the level is measured like right there onto this. So we don't have to do the same thing as we did in the previous example where we had a mixed liquid thing where we had to go for the thermometer and we had to swim down. We could just trust that distance right there, that 3.1 feet, which is a lot, is going to be the pressure difference that we can reliably choose between here. All right. So we want to find the flow rate, determine the flow rate, and this also requires iterations. You can kind of see I've already marked up this thing from a previous work. We will look up for this particular temperature, right? We want to adjust for the temperature, and so we'll find that the water is 1.896, and I'm going to use we're using slugs instead of the pounds mass here. I can also find my dynamic viscosity is going to be 8.315 E minus 6. And once again, I'm using a system of units from Munson. And I think this problem is actually from Munson. This figure is from Munson. But if you were to use Sengel and you were to look this up, I'll give you an example right here. You can go to the table A3E. All right, so let's see, we'll go to A3E. This is A9A. Hopefully it's right there. All right, so here's properties of saturated water. Here's 160 degrees Fahrenheit, and you come over for the dynamic viscosity, and you would get that it's 2.675 e to the minus 4 for the liquid phase, right? And these are pound mass per foot second. If you divide this by 32.2, you get the same viscosity as I do, right? So you don't need to divide by the acceleration of gravity. You could just use this one, whereas in the other, the pound mass, you'll have to, right? So just be aware of that. The delta P that I want to have, so this is like P2 is where we want to get to versus P1, which is over here, right? So we have the delta P is going to be equal to H gamma. So we need to use the correct rho right in there. So that's going to use rho times G for this. So we have 3.1 feet, that's we're given, times the density, 1.896, and we need gravity, 32.2. And what that's going to give us is 189.3 pounds per square foot. We also want to know our beta, and that's going to be 2.5, right? So 2.5 inch is the nozzle diameter, that guy, and the pipe diameter is 3.8. So we'll end up with 0.6579. Let's look for the mid-range right here. I guessed 0.98 is maybe a, I don't know, worthwhile guesstimate off of this thing. So I'm going to guess a CD equal to approximately 0.98. Preliminary stuff, a lot of times we're going to need the area. So I go area 1 is going to be pi over 4. And remember that these are given in inches. So 3.8 divided by 12 squared gets 7.876 e minus 2. foot squared, A2, pi over 4, 2.5, 2.5, yeah, divided by 12 squared. And so we get 3.409 e minus 2 feet squared. So we're ready to take our initial guess. Guess. I can't spell the word guess. And that, remember, this is the equation that we're using. This always is based on A2, by the way, from the derivation of it. I don't know if we emphasize that. But we have 2 times this delta P. P1 minus P2 is fine. Density, and then 1 minus beta fourth. Right. Get rid of some of that. So here's our guess. 0.98. Area 3.409 e minus 2. Square root of 2. And then we have the 189.3. The density 1.896 in slugs. And we have 1 minus, and here was our ratio, 0.6579. Fourth, I'm going to bracket. So our initial guess is equal to 0.5234 cubic feet per second. Something that's really good to do is to figure out what this is. We probably won't have to do too many iterations, but we should. This was a guess, and we needed that to be able to get this volume flow rate, so we could get the velocity. That's a guess, right? So we take that guess, and this is the upstream velocity, so we need to take it A1. So we have the 0.5234, and divided by our area 1, 7.876 e minus 2. And so we have 6.645 feet per second. So we take a Reynolds number. That's going to be rho VD divided by mu. So our rho is 1.896. Our velocity we just found is 6.645. The diameter is going to be the upstream, so it's going to be the larger pipe, but it's divided by 12, remember. And our viscosity is 8.315 E minus 6, and those are pounds seconds per square foot. And so we get 479,826. 479,826. And if we wanted to look up right up in here, so we go 479,826, and we want to take the log of that. We get 5.68. So you can kind of see where I have done this already. 5.68. We come up to here, and we kind of see we want to draw a line that's sort of in between these two, because we have a 0.8 and a 0.6, but we really need a 0.6579 curve, so it's somewhere in there. So we can see we're pretty darn close. Like, we don't really need to go too much further. We made a pretty good guess. But if we have like our first iteration, we take, well, let me say, so I can actually use this equation like I mentioned before. We can use the equation that we get out of Sengel. Let's see, where did we go? Right here. He's up here somewhere. This is the easy way to look for it right here. We can take this equation, right in there, CD is equal to 0.9975 minus 6.53 beta raised to the 0.5 and divided by Reynolds number raised to the 0.5. All right, so we could plug that in there, And let's just say that we plug the thing in. And what we end up with is getting is 0.9899. Great. So this is the, I don't know, call it the first iteration right here. So we can have now the second one. So the first was a guess. This is the first iteration, 0.9899, and multiply it by 0.5340, and we had 0.5286 cubic feet per second. Did I do that wrong? Yeah, no, I got it right. Okay, cubic feet per second. By the way, this is 1.01% off from our initial guess. Not too bad. So we could take the velocity, 1 of our first guess, which is just going to be that guy over A1, remember. And we end up with 6.712 feet per second as opposed to 6.45. We can get a Reynolds number of 484,650, which will give us a discharge coefficient. Well, let's go first right here. That's another first of 0.9899, which is the same thing that we got before, right? So we don't need to do any iterations. So this right here is our answer. But this is a liquid in US units, so we almost always want to try to go in gallons per minute. So here is a 0.5286, 7.48 gallons per cubic foot. This is, by the way, this is cubic feet per second, right? Cubic feet per second. So we go 7.48 gallons per cubic foot, 60 seconds per minute, and we end up with 237 gallons per minute. Boom. And so there you go. I'm getting tired. It is 10:20 at night. Okay, I got plenty of time before they lock up the building. But we'll go on and do another example in the next video.